Hi guys. So in the previous concept we were discussing about circular motion under motion in two dimensions. So to describe a circular motion we need different terminology. So that we got it from angular displacement, delta theta equal to delta s upon r. So here delta s equal to arc length, r equal to radius. Then after we define that angular velocity omega equal to the rate of change of angular displacement d theta upon dt. This is the instantaneous angular velocity, and from this if you can do the differentiation for this, I can write the angular velocity, and for angular acceleration so that we denoted with alpha equal to d omega upon dt, the rate of change of angular velocity. And apart of that we got a relation from the relation between linear velocity to angular velocity, that equal to v equal to omega r, or if you can write this in a vector notation, v bar equal to omega bar cross r bar. This is equal to v equal to r omega. Not only that, we got one more relation between linear acceleration and angular acceleration. Linear acceleration a equal to alpha times r, radius times angular acceleration, or in vector form a bar equal to alpha bar cross r bar. So this is the basics of to describe circular motion: angular displacement, angular velocity, and angular acceleration. Apart of that, these relations. So these relations play a very important role to get the final results. Relation between linear velocity to angular velocity. So today's class I would like to discuss a new concept regarding this, which is known as a centripetal acceleration. A centripetal acceleration. So let us understand this. So let us try to play this small video. You might be seeing this kind of activities or these kind of actions in so many places, especially in circus, which is known as death wheel. So observe this carefully. So he's trying to rotate the car in uniform circular motion. Yeah. So the car is moving in a circle of certain radius, is moving around this particular radius. Now if we can take exact point, this is the radius of circle R. Now he is having angular velocity and angular acceleration. The car is having angular velocity and angular acceleration. Now to define centripetal acceleration, so acceleration we define as change in position. Since it is circle, so in the circle the car is changing its position every time. Suppose this is a point A and this is another point B. So it is changing its position. So this is defined as angular displacement theta. And if that is position, where is the velocity? If you draw a tangent at here, point A, and another tangent at here, that is point B. So these two represents velocity at here and velocity at here, v1 and v2. Here be careful, because even though it's uniform circular motion, velocity magnitude might same, but the direction is different. So that's the reason here I represented v1 and v2. I could have write v and v itself, but here we mentioned that v1 and v2 because in circular motion the magnitude of velocity may same, but the direction is changes. If v1 and v2, these are the two velocities. So where is the change in velocity? So we know how to add that vectorially. Suppose this is velocity v1, another velocity tail I will bring at here. So this is velocity v2. Now I hope you got that resultant velocity. The resultant velocity, this is the resultant velocity delta v. Now delta v equal to v2 minus v1, change in velocity. Now here you can see that change in velocity with respect to time, delta v upon delta t, that gives an acceleration. And in this particular case, in this uniform circular motion, this acceleration will act towards to the center. So the acceleration of the car direction, since it's the radius, not only the radius, the acceleration directs towards to the center. Now this acceleration is known as centripetal acceleration. Centripetal acceleration. Let us see how this acceleration directs towards to the center. Or if you remember, on this circular motion, on that vehicle, some force is acting towards to the center. Do you guess which force is that? The force which is acting towards to the center. And this force is also responsible to not to fall the vehicle all the way down. Yeah, if your guess is correct, this force is centripetal force. To calculate the force, and if you recall, force formula F equal to ma, mass times acceleration. So I can get the direction of force until unless if I do not know the direction of acceleration. We know about the centripetal force. Now that centripetal force magnitude equal to m times acceleration, but its direction, it's acting towards to the center. And here that direction comes from this little component which is known as centripetal acceleration. Centripetal acceleration. So if you can define centripetal acceleration like this, a body undergoing uniform circular motion is acted upon by an acceleration which is directed along the radius towards to the center. Again I am repeating, a body undergoing uniform circular motion is acted upon by uniform circular motion is acted upon by acceleration which is directed along the radius towards to the center of the circular path, and this acceleration is known as centripetal acceleration. Now that centripetal acceleration directs towards to the center, then that acceleration causes a force obvious, so that leads to the centripetal force. So today's class I would like to give a little small expression for the centripetal acceleration. To derive an expression for centripetal acceleration, suppose let me take a small circle. Oops. So this is circle. The circle is having a radius of r. So from here, if you can take its radius r. So here it is center. So this is related to point P. After some time, if an object is moving in the circle, after some time the object reaches to a point which is at Q at here, and this we define as delta theta angular displacement. And if I draw a perpendicular from here to there, and this becomes to me as arc length. This time if we neglect the curvature of circle, so the distance between 2 points, that becomes delta s. So we can define that arc length, the angle subtended by the circle, which is known as angular displacement. And here if I take the velocity at point B, let it be this is the velocity vector. So this is showing along in this direction v1, and at point Q the same velocity, magnitude is same but direction is different. So this is velocity v2. And if circle is having an axis of like that, now if I add the two vectors, if I can add the two vectors, suppose if they are like that from A, so this is a point, adding the velocity vector I am considering another point A. So this is velocity vector magnitude, a point B, and from the same point if I take another velocity vector, so this is to a point C of another velocity vector v2. If this is angular displacement delta theta, don't be confused, this is apart from the circle only, but I drawn at here to show separately. And if we can add the two vectors, we can get the resultant. So this is the resultant vector. I can highlight that with this, yeah. So that is the resultant vector delta v. Now the arrow mark, I purposefully draw the vectors like this to show the acceleration is acting towards to the center. So don't get confused how these velocities are taken like this way, to show purposefully to get the resultant towards to the center. So we have taken that two velocities are like that, just rotate it, okay, or otherwise you need to change the circle figure. So that I hope you can do that. Anyway, the accelerations always acts towards to the center. Now from this figure we can write that from this triangle, if you can write that the BC value equal to, BC is a vector equal to how much you can, that AC minus AB bar, which equal to V2 minus V1. The resultant we are getting that from the triangle law of addition we can get it. So the BC bar equal to change in velocity delta V bar. So this we can call as change in velocity. Now if you can compare, these two triangles are similar. How they are similar? The triangle OPQ tells about the displacement of angular displacement delta theta. At the same time, at the same point P, velocity also exists. So but to do mathematics at here, we have taken that separately. That's only the mean, and we change the characters here also. But here if you can see, the delta theta is same and radius is also same. So they both are similar triangles. Don't be confused that one is represents supports this displacement, one is represents supports this velocity. Therefore in triangles, so in triangles POQ and triangle BAC, so they both are similar triangles. So if you can see angle POQ which equal to delta theta which equal to angle BAC. So delta theta is a common in the both the triangles. So this I represent triangle like that. If you do not confuse, you can make this is triangle, that you can write like that, shortcut. So angle POQ equal to delta theta equal to angle BAC, and we know that similar triangles ratios, the sides ratios are also equal. OP upon OQ equal to, this is AB upon AC. This is the property of similar triangles. And similar triangles sides ratios and one of the angle equal, there we can say that triangle POQ is similar to triangle BAC. So from these 2 points, one of the angles and their sides ratios became equal, then we give a conclusion that these two are similar triangles. Or if you do not get it at this point, suppose you can take OP is a unit radius, O to P is radius is same, the radius vector is sweeping. If you can take OP value and OQ value is the same, similarly the velocity also equal to same. So either you can take this as 1 or without taking that one, you can do it that. Or just we need the conclusion that the both are similar triangles. So if the both are similar triangles and the other sides ratios, it means PQ upon OP is equal to BC upon AB. So other two sides ratios are also equal. Now from the figure, what is the value of the P to Q? So PQ value equal to delta S and OP value equal to R. So this becomes delta S upon R, and BC value become delta V, and AB value becomes its V itself. So these values we got it from these two figures. BC value equal to delta V, and AB value here you can take as velocity magnitude, don't consider as direction, just AB magnitude of velocity. Magnitude of velocity, not the direction. If you take the direction, again we need to insert as V1. Now this is the final expression I needed here. Now if we can rearrange these terms, if I can write the delta V equal to delta S upon R times V. Now that is a change in velocity, but we want the acceleration. To get the acceleration, I need that delta V upon delta T. Just divide both sides by delta T. So if you can divide on both sides and delta T, so here I can write that V upon R, this is delta S upon delta T. Now if you can take limit, here you can do the division, divide by delta T on both sides, and take limit, that is also delta T tends to 0. So this side becomes limit delta T tends to 0, delta V upon delta T equal to limit delta T tends to 0, delta S upon delta T times V upon R. Now limit delta T tends to 0, delta V by delta T, we can write that dV by dt, and this time it becomes to as ds by dt times V upon R. Now dv by dt, rate of change of velocity, we can write that as acceleration A equal to ds by dt is nothing but rate of change of displacement. We can write that velocity V itself times V upon R. So finally we got an expression, acceleration A equal to v square upon r. And we know we want at here centripetal acceleration, means angular acceleration. So since v equal to r omega, so this is a relation between linear velocity to angular velocity, v equal to r omega. So substituted there, a equal to r omega square upon r. So if you can cut that, we can get omega square times r. So a equal to omega square r, which is the expression for centripetal acceleration. So this is the magnitude of acceleration expression. So omega is nothing but angular velocity and r is radius. Therefore the centripetal acceleration equal to omega square times r. So the above expression gives the magnitude of acceleration of the particle in the uniform circular motion. So what about the direction? So to get the direction, we need to look at here. So when delta t tends to 0, the angle delta theta approaches to 0. So this is the reason the acceleration is always acts towards to its center. So as v1 and v2 is directed towards to the center at point P, the acceleration always directs towards its center, that is known as centripetal acceleration. Now this is the final expression for magnitude for centripetal acceleration. Centripetal acceleration magnitude, and direction it's towards to center. So this mathematical derivation is not that much having weightage, but you remember that formula. So whether you practice the derivation or do not do, it doesn't matter. But when it comes to formula, so we can use all of a sudden this formula as a centripetal acceleration. So this is all about the centripetal acceleration.